everyone to the 35th edition of the Flow seminar series, Flow Talk. Flow stands for Federated Learning One World Seminar, conveniently displayed on this slide in the middle. Flow is an online seminar series dedicated to all aspects of federated learning, and today the aspect that Eduard Gorbunov is going to touch on is distributed training and communication compression in a non-convex setting. So it's a great pleasure to welcome Eduard Gorbunov, who is a PhD student at Moscow Institute of Physics and Technology and has a bunch of other affiliations which he's not showing to us today. So it's a great pleasure to have you. Please go ahead.
Thank you a lot for inviting me to give a talk. So today, as Peter said, I will talk about non-convex distributed learning with compression. So the talk is based on our joint paper with Konstantin Burlachenko and Konstantin Burlachenko, who is a PhD student at KAUST, with Giselle Lee, who is a research scientist at KAUST, and Peter Richtarik, who is a professor of computer science at KAUST. So, by the way, if you have any questions, you can either write it in the chat, because I have it open on iPad, or you can just interrupt me, and it would be convenient for me if you interrupt me at the end of the slide. Okay, and here is the outline of my talk. I will start with a brief introduction where I will describe the problem and compressed communications. I will introduce the compressions. After that, I will focus on quantized gradient descent, which is a simple and popular approach to use compressed communications in distributed optimization. Then I will mention Diana, which is a more sophisticated approach to handle compressed communications. And then I will present new methods developed in our paper. This is Marina, variance-reduced Marina, and Marina with partial participation. And in the end of my presentation, I will show you some numerical experiments with these methods. Okay, so let me first introduce the problem. We consider a distributed optimization problem. Here we have, we want to minimize some function f, which is a finite sum of its average of n functions. And here x is parameters of the model, d is number of parameters, and n stands for the number of workers or devices. And each device has an access to its own data and it can construct a local loss function fi(x). And these functions can be arbitrarily heterogeneous. So in this talk, we will not assume anything about homogeneity of the data that devices have. And we will consider, in the paper, we consider two cases. The first case when fi is an expectation, and this distribution di can depend on the client. And we also consider a finite sum case as well. So when local loss functions are also finite sums. But in this talk, I will present the results only in the finite sum case, when the local loss functions are finite sums. But in the paper, you can find the details about the online case, expectation case as well. Okay, so it seems that there are no questions. And typically in such systems, communication is a bottleneck when we want to minimize this function. And it's classical federated learning set. So there are a lot of different ways how to handle communication bottleneck. And the first one, for example, is to change the topology of the network, for example, consider decentralized approach. Or another popular technique in federated learning is doing more work on each device in the hope of communicating less. And it leads to very popular methods like local SGD or federated averaging. But in this talk, we will focus on another way how to handle the communication bottleneck, and it is based on communication compression. And for example, instead of sending dense vectors like this, devices can send compressed or sparse vectors, applying some compression operator Q to the input vector G. For example, here it is realization of so-called rand K operator, which will be defined on the next slide. Okay, we studied this approach. And let me also introduce the unbiased compression operator, or we will call it just quantization. So it's a stochastic map. So it takes X d-dimensional vector as an input, and the output is Q of X. And this Q of X on average equals X. And also we assume that the variance of this estimator is bounded by the squared Euclidean norm of the vector X times some number omega. This number omega measures how rough the estimate is. So, for example, if you consider rand K operator, and in this case, K equals 2. So in this case, we also have, we pick just K components uniformly at random. In this case, it's K equals 2. And we also multiply the resulting vector by some number which is needed for unbiasedness. And actually, the denominator here is number of components we want to keep in the vector, or and the numerator is number of dimensions. So it's number of parameters. And omega here for this operator equals d over k minus 1. So in this case, in this special case, d equals 5. So this is roughly how run K works. Okay, are there any questions? It seems no.
I don't see anything yet. If
okay.
I do see, I'll certainly let you know.
Okay, then we can go next and consider the natural approach how to introduce compressed communication, and it is based on quantized gradient descent. Here, at each iteration, server broadcasts the parameters to the workers. Then workers compute the gradients. Sorry, here is a typo. I should have here nabla f2 and here nabla fn.
Well, you're just assuming the homogeneous data setup, right? Implicitly.
No.
Okay.
It's just a typo. So here yes. So here devices compute the gradients using only their own data. So here it should be nabla f2 xk, like here nabla fn xk. So after that, devices quantize the gradients. So they apply some unbiased compression to the gradients and send these vectors, the resulting vectors, to the server, and server performs the update using this formula. Actually, it looks like actually it can be seen as an SGD update if we define GK as an average of this vector's GI case. And after that, server, so the steps 1 to 5 are repeated. And one might ask the following question: how quantized gradient descent converge? How fast it is? And before that, we need to introduce some assumptions. So, as I said in the introduction, we consider non-convex optimization problem, but still we need to assume something, because otherwise we cannot prove anything. So we, first of all, we assume that there exists uniform lower bound for the overall function f, which is the average of n functions. And we assume that each individual local function is L smooth. By the way, in this talk, we will not focus on how smoothness parameters appear in the bounds, but we will have it only here on this slide. Okay, it seems that Allure.
There is a question.
Yes.
I have trouble figuring out whose question that is. I can see now.
It's me, yeah. So my question is whether there exists practical examples of function f where fx is not lower bounded at all. So usually if you talk about loss functions in machine learning, fx is always bounded by 0 from below, for example.
Yeah. So the honest answer, I cannot remember such functions right now. You mean some functions that are important in practice? Okay, so actually it just means that this assumption is not very restrictive. Okay, linear functions are not lower bounded. Okay, but we can it's the message in the chat. Yeah, they are not lower bounded, but we consider unconstrained minimization problems, so it's not interesting case when the function is linear for unconstrained minimization. Okay, so are there okay, I think. Okay, I think I can consider the next slide and show you the complexity bound for quantized gradient descent. So to achieve epsilon stationary point, which means the following, quantized gradient descent means the following number of communication rounds. And here, capital O hides not only numerical factors, but also smoothness constants of the problem. And we see here that the leading terms proportional to the epsilon to the power minus 4, which is bad. But also here, let me remind you that omega is a quantization parameter that describes the variance of the unbiased compression, and delta 0 is difference between the functional value at the beginning and between the lower bound. And this delta f star can be so in general it's not 0 this guy, because we do not assume that functions are heterogeneous. So, and the natural question, how to improve this bound? Because, for example, when we apply gradient descent, it has communication complexity proportional to the epsilon to the power minus 2, which is much better than this. But gradient descent needs to send dense vectors. So can we take advantages both from quantized gradient descent and gradient descent? And the answer is yes. And for example, one can use the method called Diana. So the scheme of the method is the same, but the difference is how to choose GIK. So in quantized gradient descent, GIK it's just quantization of the local gradients. And in Diana, the estimator is more sophisticated, and instead of quantizing the gradients, it quantizes shifted gradient. So we shift the gradient at the current point by some vectors HIK, and these vectors are updated during the process using this formula. And for example, in the convex case, it just estimates the gradients of the individual local loss functions at the optimum. So these guys are needed to learn the gradients at the optimum. Yes, and moreover, one can notice that actually devices just need to send vectors in the orange boxes, and both for QGD and Diana. So why don't they need to send these vectors HIK? And the answer is simple, because the server can obtain HK, which is the average of HIKs, using the information about this quantized differences. So actually, one can implement Diana without sending these shifts. The devices are needed to this. The server just needs to know what are the initial shifts at the beginning of the optimization, and after that it can update them using this formula, but and using only only quantized information. And Diana converge faster. And it means that it finds epsilon stationary point after this number of communication rounds. And clearly here, as before, capital O hides smoothness constant. And clearly here, we have only epsilon to the power -2 dependence on epsilon, so on the accuracy of how small is the norm of the gradient is. And but the dependence of omega on omega is slightly worse, because I will show you on the next slide. The dependence on omega, the dependence on epsilon is better, but the dependence on omega is worse, because here we have omega over n, and here we have omega to the power 3/2 over n. But when epsilon is small, this in this bound, in this complexity bound, these terms dominate this one, and we see that Diana, the complexity bound for Diana is better. So I think it's a good time to make a pause for questions. However, I do not see any questions in the chat.
I don't have a question. I'm just here to facilitate question asking. So please, everybody, if you're new to Flow, we really love engaging with the audience. Please do ask questions. We'd like you to ask in your own voice, ideally. So please don't hesitate to stop the speaker in this talk or any other future talks at any point in time. This is what we want. So there's a question, and let us unmute Konstantin so that he can ask the question in person. There you go.
All right, can you hear me?
Yeah.
Okay, so my question is, do you have any intuition why quantizing differences is better than quantizing the gradients themselves? Why the rate improves?
Yeah, it's a nice question. So first of all, when these shifts are needed to approximate the gradients at the point where we converge. So gradients of individual loss functions where we converge. So when we quantize the difference, the error is smaller because we know that the variance of the quantization operator is relatively bounded by the norm of the input vector. And therefore, when we quantize the difference, which goes to 0, we obtain tighter estimate of the gradient, because on average, this estimate, on average, this guy equals number of fi xk by definition of q, and here we will have bigger variance of the vector. That is why this estimator is more accurate. And yeah, and the main intuition is that these vectors are when k grows, they become closer to the gradient of fi to at the point where we converge. So in the convex case, at the point where the function has its optimum, and in non-convex case, to the gradient at the point where to the gradient at the stationary point.
So I would have a question while we're waiting for others to ask. Can you go just one click further? Yes. So could you give also some intuitive explanation of what this update for H means? So you explained that when you quantize the difference, only the quantized vector needs to be updated. But why the update? Why does the update look this way?
So thank you for the question. So one can think about this is that this vector. So we perform some kind of okay. So the best approximation of the gradient at the optimum would be the gradient at the current point, but we, for some reason, apply this update rule, and it can be seen as the gradient descent run on the problem. We like stochastic gradient descent run on the problem run on the problem of minimization the difference between the minimization of the squared norm of the difference between this vector and some minimization variable x. So this alpha will be a step size, and so it can be seen as one step of learning process of the best approximation of the gradient that at the optimum. It's one thing. Another thing, we can simply say that this is the old information that we have, and this update moves us closer to the gradient at the optimum, because gradient at the current point it is some approximation of the gradient at the optimum. But actually, this question is good because it is related to the new method, Marina, because I will clarify later.
Okay, thank you. And I don't see any new questions at this moment. So please feel free to continue.
Okay. Thank you for the questions. And we stop here. I show you the complexity bounds for Diana and QGD. And so the natural question, is it possible to get better rate? And the answer is yes. And in our paper, we proposed a new method called Marina that has better rate. So as before, we consider the same update rule, but the devil is in the details. So we need to clarify what is GIK now. And recall that GIK for Diana looks like this. And for Marina, we substitute this local shift by the best local shift that we have, and clearly it should be the gradient at the previous point, because it is the best approximation of the gradients at the solutions that we have at the moment k. And for now, just forget about the first line and look at this line. And so the difference between Diana and Marina is that we change the learnable shift. So instead of HIK, we just put their gradient at the previous point. Okay, Elnur is asking, is there a typo? Which one?
So let me unmute Elnur so that he can explain what he.
Yeah, so sorry. So my question is whether it seems like, I mean, doesn't it sound natural that the gradient at point xk minus 1 this here should be replaced by jk minus 1?
It's replaced by HIK is replaced by the gradient at the point xk minus 1. So in some sense, it is better approximation of the gradient at the optimum than HIK, because HIK is a learnable shift.
So at previous point you store not only GK minus 1 but also the gradient itself.
Yeah, because at the previous iteration we already computed the full gradient. So we computed the full gradient at iteration k. We know the gradient at the previous iteration, so we need just compute this gradient, and for free we can substitute the gradient at the previous point from the new gradient. Okay, thank you for the question. So now I told you that forget about the first line. Now I want to discuss the updates. Okay. There is another question. Is the learnable shift comparable?
I'm unmuting Francesco so that he can ask himself. You're unmuted.
Yeah, can you hear me?
Yes.
So I was wondering whether the idea behind this shift in the gradient is comparable to the advantage function in reinforcement learning, where you try to estimate the returns based also on an estimate on your returns using like the value function.
So actually,
okay, so maybe it's like a specific.
Yeah, I don't know. I didn't think about the relation.
Okay.
So
okay, it was just a possible connection with the same, basically the same thing seen in a different topic.
Yeah. So probably it would be great if you can share the link in the chat, and for example,
sure.
we can look at this after the talk, for example, during the discussion.
Okay.
Thanks.
Thanks.
Okay, so now I want to focus on the whole update. So here, the idea is as follows. With some small probability, devices just send dense vectors. They just send full gradients of Fi at the current point. And it has happened with very small probability. And with larger probability, devices are needed just to compute the quantized gradient differences. And as before, as in Diana, devices have to send only vectors in the orange boxes. So with probability P in Marina, devices send dense vectors, uncompressed vectors, and with probability 1 minus P, with large probabilities, they send only quantized gradient differences. GK minus 1 is not needed to be sent because the server already knows this vector, because GK here is defined as an average of GIKs, and server knows it from the previous iteration.
So is this supposed to be GIK minus 1? Is it missing subscript I?
So no, probably. So it does not matter actually algorithmically, because it does not change anything in the algorithm, because I use this representation just to fit this framework. Yes, and in the method, devices just compute either this thing or this thing, and they never add GK minus 1 to the vector, to the quantized gradient difference. GK minus 1 is added to the average of these quantized gradient differences on the server side. So when the server computes GK, namely this average. Okay.
Yep.
And the main difference between, and another difference between Diana and Marina is that in Diana, GK is an unbiased estimate of the gradient at the current point. So it's meaning that the expectation of GK with fixed XK is gradient at the current point. And Marina is a biased method. And actually, this is not very usual phenomenon in optimization when bias helps to get better rates, but actually in non-convex optimization it is, and yeah, but in general optimization it is not. And let me share what complexity bounds we proved for Marina. So to find epsilon stationary point, Marina needs this number of communication nodes, and here the dependence on epsilon is epsilon to the power minus 1, which is optimal for gradient methods. And omega is defined. It is here. Dependence on omega is just linear. And next, here this result is derived for the choice of P, probability of sending dense vectors. To the choice of P equal 1 over omega plus 1. And we assume here that it is equal to the zeta q over d, probably with some constant. And zeta q is the expected density. So it's supremum over all x's of expectation of zero norm of the quantization of x. Zero norm means the number of non-zero components of the vector. So that is why we call it expected density. It's expected number of non-zero components in the quantized vector. And this assumption actually holds for such famous quantization operators like RandK or L2 quantization. So it's quite natural. And when we choose P in this way, the expected number of transmitted transmitted components per worker is equal is the same as in Diana when we apply Q, the same quantization operator. So this probability is needed just to balance this the cost of communicating this one, this vector, and this vector. So on average, the cost is like when we communicate only this vector up to some up to numerical constant 2.
So we have a question by Imeric. I unmuted you.
Yes, thanks. Hi, Eduard. Just
Hello.
Can you hear me?
Yeah. Hello, Imeric.
Yes. A simple question. So in your strategy, you choose to communicate without compression with a small probability, right?
Yeah.
And could you improve Diana with such a trick on top? I mean, it's unclear. I don't see how we could, but would there be a way to improve the algorithm Diana by communicating someone sometimes without compression?
Yeah. So thank you for the question. Actually, I didn't think about this, but I think that in Diana we pay for let me show you this slide. So here we have the comparison between the race of Diana and Marina. So in Diana we pay by extra square root of omega factor because we run the let's say. So because we learn these shifted vectors. So I think that the reason that why we have worse dependency is because of this update for how we choose HIK plus 1. So it seems that if you apply the same trick for Diana, it will not remove bad dependence on omega. I think I didn't try to do that, but I think that it will not improve this bound. Okay, thank you for the question.
So I if I may interject here, so it is possible to think of Diana as also doing what you just said, because you could combine Diana with a more complicated compressor, which would do this, that this communication with some small probability would actually happen in that way. So I can imagine this is possible.
It's like a special case of quantization.
Yes.
Okay.
Yes. But I don't think how that would lead to improved result. So I don't think that's really what's causing the difference in complexity. I think the difference is really because one is not learning, as Eduard said, and that one is really using the loss gradient, and this is a very highly structured special biased compressor, and that is really critical.
Mm-hmm. Thank you for the comment. And
there is one more question by Igor. So you are unmuted, Igor.
Yeah, hello. Can you hear me?
Hello, I can hear you.
Okay, that's great. The question, I have two questions, and the first one: why do you choose this probability that you showed before? Is it, just to obtain, beautiful factors inside the complexity result, or it is optimal in some sense?
It's in some sense it is optimal because here we use probability proportional to the ratio between expected density and the dimension d. And when we choose P this way, then we equalize in some sense the cost of communicating this and this, because on average, we will pay D times zeta over D plus zeta times 1 minus P. So on average, we will send 2 times zeta components. That is why we choose P like as here. Yeah.
Okay, but the question is this, for example, we'll use a rand k with a fixed k among the learning process. Thus, it will be this probability, will be proportional to k divided by d, and this means that the lower k will lead to lower probability to compute.
Yeah, that's natural, because this way, let's say we take here k equals 1. Then with probability 1 over d, we send d components, and with probability 1 minus 1 over d, we send just 1 component. And it means that on average, we send just 2 components each time.
Okay, and another question is, you said that your method is optimal in terms of its dependence on epsilon.
Yeah.
But is there any lower bounds which estimate the optimal dependence on omega?
So,
for example, can we do better? I mean, can we now improve it possibly in theory? This dependence on omega.
So I think without any assumption on quantization, we cannot, because we can think about derivative-free optimization. So, or just, for example, when we compute directional derivatives, in that case, omega will be something like d minus 1. And so it is known fact that without any assumptions on the structure of the problem, the dependence on the dimension for zero-order optimization will be proportional to d. So I think that this means that we cannot improve the dependence on omega.
What about dependence on n?
Well, dependence on n. Actually, here I don't know. I don't know lower bounds.
So I personally have a guess that there is a matching lower bound, but we didn't try to establish it.
Mm-hmm.
The reason is that somehow, in some sense, Marina is to Diana what Sarah is to SVRG or something like this, and we know that Sarah in the non-convex case is optimal, and so I would believe that Marina would be optimal in this setting, but we did not attempt to prove it.
Okay, thanks.
So there's a question by Ming Xing. I unmuted you. You can ask your question.
So my question is, how do you choose the optimal P in the experiment?
Sorry, what do you mean by optimal P? So you mean why do we choose this P, or what?
Why do you choose this P?
Okay. So yeah, thank you for the question. And we choose this P because let me recall that zeta is expected density. It's how much components how many components the quantization of x has on average. So, and let me go back to the update rule of Marina. So with probability 1 minus p, we need to send zeta components. And with probability p, we need to send d components. So it means that to equalize these things, so we need to choose p equals zeta over d. So probably with some constant. And in this case, the cost of communicating GIK, of communicating this or this, on average, will be the same as the cost of communicating just compressed gradient difference, but with some numerical factor like 2 or smaller than 2. So, have I answered your question?
And in your experiment, how can you compute the omega? The omega can be computed in the real data.
So omega depends only on the choice of the compression operator. So since we are choosing the compression, we can compute easily the omega. So for example, for RandK operator, we know the exact formula for omega. Let me show you this one. For RandK operator, for example, we have this formula that omega equals d over k minus 1. D is number of components, d is number of dimension, k is number of components that we choose. So that is why we can use omega in the formula for p.
Yeah, okay, thank you.
Thank you for the question. Okay, so let me go back. Probably I need to accelerate myself. Okay, so we stopped here. On the slide is comparison of the rates of Diana and Marina rates. So the improvement is in the square root of omega factor, and everything else is the same. But neglecting the smoothness parameters, so we are not focusing here on smoothness parameters, but one can check the details in the paper. Okay, and what's next? For example, we considered here full gradient methods. So the natural extension is to consider stochastic gradients methods, and it leads us to variance reduced version of Marina. So in this setting, we will consider the case when Fi is average of m functions. So for simplicity, we do not assume that m depends on the worker I. So for simplicity, we assume that m is the same for all workers. And as before, the update rule will be just the SGD update rule, but the difference is in how we compute GIK. So let me recall you that GIK for Marina was computed like this, using this formula. And for variance reduced Marina, we just substitute full gradients by stochastic gradients. For example, here we substitute the gradient of Fi by gradient of Fij, where J is sampled uniformly at random from 1 to m. And everything else is the same. So just this small modification. Okay, Francesca, thanks for the link in the chat. So it's just one simple modification. So instead of computing full gradient, we compute stochastic gradient, just one gradient, gradient of one function in the sum, for example. And Yeah, here is M. And what about the complexity bound? And the complexity bound changes as follows. So VR Marina requires this number of communication rounds or oracle calls per node. In this case, when batch size equals 1, it's the same thing. And we again have epsilon to the power -2 dependence on the accuracy. And in general, when M is smaller than omega plus 1, we will have the same communication complexity like as in Marina. But when M is big, the leading term is this one, and dependence on omega will be better. But the price for that is large M here. So in general, we cannot improve the communication. So we cannot improve the dependence on omega, but yeah. So number of communication rounds cannot be better than omega over square root of n over epsilon to the power 2. But here we compute just stochastic gradient. And the choice of P here, we need to choose P, not just to balance the number of send components. We also need to balance the oracle number of oracle calls. So let me go back. Here with probability P, we compute full gradients of Fi, and with probability 1 minus P, we compute just stochastic gradients at the current point and at the previous point. So and also quantize this thing. So now we should care not only about the communication cost, but also about oracle complexity when we choose P. And that is why here we assume that both things are important, both communication complexity and oracle complexity, and choose P this way. And let me compare the rates of Marina and VR Marina. So we see that in Marina, number of communication rounds for this problem and number of oracle calls per node are not the same. So number of oracle calls per node is m times bigger than number of communication rounds, and it is natural because we compute the full gradients at each iteration. But for VR Marina, we have with batch size 1, number of communication rounds and number of oracle calls per node are the same, neglecting numerical factors. And here we have better dependence on M in terms of oracle complexity. And actually, without compression, for example, when omega equals 0, which means that with probability 1, Q of x equals x. So no compression. We will have here something like 1 plus square root of m over square root of n over epsilon to the power -2. So, and actually it is optimal rate. It is optimal rate. For example, if you take n to be 1, we will get the same rate. We will recover the rate of known methods like Sarah, Spider, or Page, which are the optimal methods for such functions, for finding epsilon stationary points of such functions. Yeah, and also I forgot to add that we also assume that Fij, Fij are smooth as well, not only Fis. But since we do not write explicitly in these bounds the dependence on smoothness parameters, so now we do not care. Okay, and finally, probably very quickly, okay, and also by the way, the previous state-of-the-art method for distributed learning with of distributed non-convex learning with compression was variance reduced Diana. This method was proposed in Horvath et al. In 2019, and here in comparison to VR Marina, the dependence on omega was improved, and in VR Marina, the dependence on omega was better than dependence on omega in VR Diana, and also the dependence on M is better than in VR Diana. And as Peter said, VR Marina is relates to VR Diana as Sarah or Spider relates to SVRG. So yeah, here we have square root of M dependence on M, and here we have just M to the power 2 over third. Like it is very similar to the bounds of SVRG and Spider or Sarah. Okay, and so we now finally I would like to mention.
So before you go there, I just want to say that first of all, the time is up, but that doesn't mean you have to stop because we quite often go over time. What I would suggest that people who really need to run because you're expecting this to take an hour, of course, feel free to run. We're happy to have you. If you have time, hang around. We would love to interact with you. And Eduard, you can take your time to finish this off. You don't have to hurry too much.
Okay, thanks. Actually, I do not have a lot of slides. It remains to just mention partial participation, and we actually have good background from the previous line, so I'll quickly introduce Marina with partial participation. So here we consider client sampling. So let us call IK prime the set of clients participating in communication on step K. And in Marina with partial participation, with small probability, all clients send the information to the server, and with larger probability, 1 minus p, just some subset of clients communicate with server. And this is the idea, and we can actually, the update rule is the same as before, but the difference is in how we choose GK. Here we have CK, it's Bernoulli random variable, so with probability P, all workers have to participate in communication, and also they have to send uncompressed vectors. But it happens with small probability. And with larger probability, 1 minus p, only R workers from the set IK prime participate in communication, and also they just need to send compressed gradient differences. So visually, it's very similar to Marina, but here we have the summation not over the whole clients, but only summation over the subset of clients. And we proved the following. There is a question in the chat about the choice of P. Yeah, P is different. I will show you now on this slide. So on the slide with complexity bound. Here, in the paper, we proved the following complexity. So it's to find epsilon stationary point, Marina with partial participation requires this number of communication rounds. As before, dependence on epsilon is epsilon to the power minus 2. Dependence on omega is linear, and yeah. And the difference is in the dependence on N and R. So here we choose P to be R over N times omega plus 1. So Why did we choose it this way? Because we wanted to have this property that P equals some probably constant times R times zeta over ND. And why so? And the answer is that because with probability P, the overall number of sent components is n times d. So with probability P, all workers have to send dense vectors. And with probability 1 minus P, just R workers need to send zeta components. That is why we choose P this way. Yeah. So roughly speaking, it means that on average, only 2R workers participate in communications at each step. And if we compare the rate with the rate of Marina, we will see that it is worse by the factor n over R, but the iterations are cheaper by the factor by the same factor n over R. So it is quite natural, this dependence on R. And we also tested, by the way, are there any questions about partial participation? Okay. So then I can show you some experimental, some results of numerical experiments. We tested Marina and Diana and variance reduced methods, variance reduced version of these methods on the following problem. Here, YT is either -1 or 1. It's binary classification problem, and AT is some feature vectors. And we split the data sets into 5 equal parts, each data set among 5 clients. And in the experiments, we used theoretical step sizes, and also for stochastic methods, batch size was 1% of local data. So it was M over 100. And here are the results. So we tested Marina and Diana with RandK compression operator for different choices of K. So here, these data sets, mushrooms and W8A, they have, I don't remember the exact numbers. So mushrooms is something like 100 components, and WAA, I think it's the same, something like. And we see that Marina converges faster, both in terms of the loss and the squared norm, than Diana. And it's in terms of communication, number of communication rounds, and also in terms of number of bits per worker that workers send. And also here are some results with variance reduced version of Marina and Diana, and the situation is also the same. So our theoretical findings were justified by numerical experiments. Yeah. So finally, I would like to say that in the paper, we also have a mini batch version of variance reduced Marina. So in this talk, I just consider the simplest case when batch size equals 1. Next, we also have convergence guarantees for the case when Fi equals expectation, not necessarily finite sum. Moreover, we also have the rates under Pollack-Ley ACH condition. And next, one can find in the paper explicit dependencies on smoothness constant. And for example, one can use in VR Marina non-uniform sampling as well. Next, I also would like to mention that our analysis is quite simple, and it can be modified to handle different scenarios of some combinations of partial participation and variance reduction, and so on, or different compression operators on different nodes, or different batch sizes on different nodes. So it's everything is doable because proofs are quite simple. Okay, this is all I wanted to share with you today. Thank you for the questions, for the interaction, and now I will be happy to answer new questions if you have any.
Thanks, Eduard, for this great talk. Igor Sokolov is asking first question. I'm unmuting you, and Samuel, if you could unmute everyone so that, or allow everybody to unmute themselves so that they could ask questions as they arise.
Yeah, it's enabled right now.
Eduard, first of all, thank you for the great talk. And the question is, previously said that in case we consider the identical quantization, which actually means no quantization appear, that the rate is variance reduced Marina becomes equal to the rate of page. Yes.
Yeah, well, and also it becomes actually page, some version of distributed page, but when we further take n to be 1, then the rate recovers the rate of page.
But the thing is that if we, for example, assume additionally the finite sum structure of the client loss, the variance reduced Marina does not become page algorithm, because in page algorithm with probability p we would compute stochastic gradient, but variance reduced Marina in a single node setup, and then would compute with probability p the whole gradient of a local loss function.
Actually, yeah. Thank you for the question. I think I understand the question. So here we consider finite sum case. So here in page, it is also needed to compute full gradients here with some probability when we consider finite sum case. When we consider online case, then of course there is a need to compute just also stochastic gradients, but with larger batch sizes. Or we can, if you assume some bound on the variance of the vectors, then actually if m is too large in comparison with uniform bound on the variance of the stochastic gradients, then even in the finite sum case, one can replace this by large batch computation, large batch gradient computation. But again, without additional assumptions here in page, it is also needed to have full gradient computation.
Okay, so just a reminder, you can unmute yourselves if you wish to ask a question. You don't have to raise hand. Just unmute yourselves and shout. Okay, so it seems this is it. Thank you very much, everybody, for attending. It was nice having you. And thanks, Eduard, for this great talk. And see you again next week.